We have discussed four varieties of biasing a transistor at a given current I0, and central to all these circuits is negative feedback. So far our discussion has focused on the sense of negative feedback. When you use these things in an amplifier, you also want the transistor to be in saturation region. Okay, so that means that you have to get the sense of feedback correct, as well as you have to get the bias voltages and so on correct, so that the transistor remains in saturation. Okay, now we will discuss a few of these issues. I will show all four types of setting up bias. The very first one was sensing at the drain and feeding back to the gate. The feedback to the gate has to be through a positive incremental gain, and you can do that. Of course, the variant that we used, because positive incremental gain also includes simply connecting it directly. Okay. By the way, I keep using the term gain here to describe this circuit, positive incremental gain and so on. I don't really mean that it has to provide amplification. That is, the variation at the output doesn't have to be more than the input. It can work even if it is less. What I really mean is the sense of variation of output as the input is varied for this block. Okay. So these two circuits are the same, where this positive incremental gain is simply replaced by the wire. Okay. And we also looked at sensing at the source and feeding back to the source, where the gate is biased at a fixed voltage VG0. So it really means that I have a voltage source VG0, or it's derived from a voltage divider and so on. I have I0 here. Okay. Then we looked at sensing at the drain and feeding back to the source. Okay, where we connect the current source to the drain. The gate is biased at some VG0, and an example was to use an op-amp. In general, this part of it that I will show in red, this can be any circuit that has a negative incremental gain. Okay. And lastly, we sensed at the source and fed back to the gate, and the circuit looked like this. This is the example that we took, and this I call Vs0. So that means that it is connected to a voltage source of value Vs0, or it's somehow biased at Vs0. And in general, circuitry from there to there, it can be any circuit with a negative incremental gain. Okay, so that's the idea. Now, after you do this, there are of course many realizations possible for this positive incremental gain or these negative incremental gains, and choice of these bias voltages Vd0, Vs0 and so on. After that, you have to check separately and ensure that the transistor is in saturation. So that means that Vds is more than Vgs minus Vt. Okay. So I'll show it for a couple of examples, and you can work it out yourselves from assignment problems or activity problems, and you can even create your own examples. Okay. So first of all, saturation region of a MOS transistor is defined by the drain source voltage VDS being greater than VGS minus VT. Okay. There are many other ways to put this. Sometimes this is convenient to use when you can calculate VDS and VGS. Okay. Now, VDS can also be written as VD minus VS, where VD and VS are the drain voltage and the source voltage with respect to some ground. And similarly, VGS can be written as VG minus VS, where VG and VS are gate and source voltages with respect to the same ground, minus VT. Okay, and clearly you see here that VS cancels out, and the same thing can be equivalently written as VD being more than VG minus VT. What does it say? So instead of even computing VDS, you can just compare the drain voltage with the gate voltage. What is this saying? The drain voltage has to be more than gate voltage minus VT, and VT in general can be negative or positive, although for the most often used variety of transistors it is positive. Okay, so we will continue the discussion assuming that VT is positive. So what is this saying? The drain voltage can go below the gate voltage, but not by more than 1 VT. Okay, so one way to visualize the transistor going into triode region is to imagine this separation between the drain and source in terms of voltage. Of course, the voltage separation between drain and source becoming too small. Okay, so if you have the drain at the same voltage as the source, VDS will be 0 and you will be operating at the origin of the ID/VDS characteristics. It will be in deep triode region. Okay, as this voltage, as this separation increases, it goes towards saturation region, and if the separation exceeds VGS minus VT, it will be in saturation region. Another way to think about it is the drain voltage going below the gate voltage. That itself is allowed because VT is positive, so VD has to be greater than some voltage that is smaller than the gate voltage. In our examples, we have been considering VT of 1 volt, so VG minus 1 volt. So if VG is 3 volts, this means that the drain voltage has to be more than 2 volts. It can go below the gate voltage, but not by more than 1 threshold voltage. Okay, so that's another way to think about it. And if you rearrange these things, you can also see that VGD has to be less than VT. Okay, that's another way to think about it. I mean, it's just rearrangement of the same relationship. The gate drain voltage has to be smaller than VT. Okay, all these are restatements of the same thing, but depending on the circuit configuration, one of these three relationships is actually easier to use than the others. Okay, so this is just an aside because I'm going to discuss this with respect to the circuits that we already have. Okay, the very first circuit, sensing at the drain and feeding back to the gate, this is what we had. And we know the sense of feedback. Okay, and the simplest variety was to just connect the drain to the gate, and this we know this will be in saturation region because the threshold voltage is positive. That means that VD will be more than VG minus VT, because in this case, after all, VD equals VG. Okay, so this will be in saturation region. Now another alternative which you would have seen in some activity questions, or I even discussed it in one of the earlier lessons, is to have a voltage source. Okay, so let's say I call this Vx. Then now you see that Vd and Vg are not the same. Vd equals Vg plus Vx, and Vd has to be greater than Vg minus Vt. So from these two you can see that Vx has to be greater than minus Vt. I have shown this with the positive polarity to the right towards the drain. Now this Vx could be negative, but it cannot be more negative than 1 threshold voltage. Okay, if Vx is minus half a volt, this will be in saturation region, but if it is minus 1.5 volts, this will go into triode region. Okay, so that's as far as this particular circuit is concerned, and this is true in every case. Okay, because just for biasing, for instance, in this case nothing else is connected, in this case nothing is connected to the drain, and so on. Okay, but when you turn this into some small signal incremental functionality, something will be connected to the drain. So you have to evaluate the saturation region condition separately. That's what I'm trying to say. Okay, the feedback has to be in the correct sense, and the transistor has to be in saturation for it to behave like a good amplifier. Let me consider an example where we sense at the drain and feedback to the source. We have the MOS transistor. To sense at the drain, we connect a current source I0, and the drain current ID is the current through the MOS transistor. We have the gate voltage VG0, and the feedback loop is completed with some block which has a negative incremental gain. I'll use an op amp with this polarity. We saw earlier that this maintains negative feedback around the transistor as well as the op amp, and that's generally the case. Okay, and this point is connected to some fixed voltage. Let me call that VD0. Okay, so now because of negative feedback around this, the current through the transistor will be I0. And how does that happen? By having the appropriate value of gate source voltage. Now, assuming that the transistor is in saturation, the gate source voltage would be the threshold voltage plus square root of 2 times the drain current divided by the current factor. Okay. So now the voltage at the source would be VG0 minus this voltage, minus VGS, which is VG0 minus VT minus square root of 2ID by mu n C ox W by L. Okay. Now the drain voltage here, what is that? You can figure out the value by realizing that the op amp's inputs are virtually shorted because the op amp is in negative feedback. So these two inputs are at the same voltage. So the drain voltage is VD0. Okay. Now how do you verify whether the transistor is in saturation region? By comparing the drain voltage to the gate voltage or drain source voltage to gate source voltage. In this case, it's easier to compare drain voltage to the gate voltage. We know that VD0 has to be greater than VG0 minus VT for the transistor to be in saturation region. Okay. So what decides whether the transistor is in saturation in this particular circuit are the values of VD0 and VG0. Okay, and you have to choose them appropriately so that the transistor is maintained in saturation. Okay, and of course there are circuits where you may want the transistor to be in triode region. Again, you have to choose the values of these things appropriately so that the transistor remains in triode region. Okay, so in summary, when you bias a transistor at a constant current, you are establishing a negative feedback loop. We know how to make the loop to have negative feedback. That is, eventually the circuit should settle to a point where the drain current is exactly equal to the desired current. Okay. If the drain current is more than the desired current, somehow the gate source voltage must reduce, and if the drain current is less than the desired current, the gate source voltage must increase. Okay. So negative feedback ensures that. But of course, negative feedback only tells you in which direction to vary things. The absolute values of voltages are also important to maintain the transistor in saturation region, and you have to pick that appropriately. Okay. The negative feedback loop can be completed by a variety of means. In each case, you have to separately check and make sure that the transistor is in saturation. Okay.